Harvest begins long before the stalks reach the mill. Fields are monitored for optimal bricks, sugar maturity, and harvest windows are planned so cane reaches the factory quickly. Mechanical harvesters cut whole stalks at ground level, strip most leaves, and chop cane into short billets that are easier to load and transport. In some regions, trained crews still harvest by hand with machetes. They cut, trim, and bundle cane for loading. Whether machine or manual, the objective is the same: deliver fresh, intact sucrose to the mill. Time is critical. After cutting, respiration and microbial action start consuming free sugar. Therefore, cane should be processed within 12-24 hours to minimize sucrose loss. Farmers and mill operators coordinate harvest routes and schedules, so trucks move harvested cane directly to the factory. Good field practice also reduces trash content, leaves, soil, lowering contamination, and improving extraction efficiency. In mechanized operations, harvesters include defoliators and toppers that reduce carryover trash. Workers inspect fields for burnt cane, controlled burning, used in some systems, and for any foreign objects that could damage equipment. Harvest, logistics staging areas, loading ramps, and temporary weigh or tally points are organized to keep cane moving. Clear communication between field crews, transporters, and the mill intake gate is essential. One delay can mean measurable sugar loss across many tons of cane. The harvest stage sets the biochemical quality and physical condition of the raw material, directly impacting every downstream step in the factory. Once cut, cane is loaded into trailers, trucks, or tractor-drawn wagons and routed to the mill. Transport may be short fields adjacent to the factory or long, requiring timed convoys. At arrival, each load passes over a weighbridge so the mill records delivered tonnage and coordinates payment or inventory. A reliable weigh system is crucial for accounting, mill throughput planning, and logistics. Before processing, technicians take samples for POL testing, sucrose content, and basic quality checks. A small representative portion of cane is crushed or pressed in a handheld polymeter device or lab centrifuge. The measured PO percentage helps estimate expected sugar recovery and guides processing decisions that day, such as imbibition rates and steam allocation. Samples also reveal trash content, extraneous materials, and whether unusually high moisture or disease affects cane quality. Transport conditions influence cane integrity. Loads compacted too tightly or left waiting in hot sun can start to heat and ferment, reducing recoverable sugar. Likewise, dusty roads increase grit contamination, which later wears equipment and complicates juice clarification. For that reason, many mills operate strict intake windows and rapid unloading procedures. Drivers and yard staff coordinate to keep cane moving from truck to tipper or conveyor without delay. Efficient transport maintains high sucrose yield and lowers operational costs across the mill. At the mill, gate cane is tipped into the cane yard or directly onto feed conveyors. Modern yards use mechanized grab cranes, front-end loaders, and tipping stations to move heavy loads safely. The central conveyor network transfers cane from yard to the mill's preparation area. Feed tables and hydraulic pushers deliver a controlled flow to the carrier, so downstream equipment receives a steady, even supply essential for efficient extraction. Trash leaves, bits of soil, and extraneous matter must be minimized. As trucks tip, leaves and light trash are blown or shaken off, and magnetic separators or simple screens remove large foreign objects. Some mills use pre-cleaners or rotary trash washers in the yard to further reduce contaminants. Keeping trash low protects rollers and screens and improves juice quality later on. The yard layout balances storage, throughput, and safety. Temporary stacks allow short buffering during minor disruptions. But long-term piling is avoided because standing cane heats and loses sugar. The feeding system includes sensors and load cells to measure feed rate and ensure the mill train receives consistent mass per hour. Operators monitor conveyors for jams, slippage, and bridging. CCTV and remote controls increasingly allow operators to manage feed remotely and to stop the line quickly when foreign objects are detected. A well-run cane yard and feeding system create the foundation for stable, high-efficiency milling. Poor yard management causes bottlenecks, quality loss, and equipment wear. Cane preparation transforms whole billets into a form that releases juice easily. This stage typically includes mechanical knives, shredders, and sometimes hammer mills. Knives slice billets longitudinally and into smaller segments. Shredders and flails tear and bruise fibers, exposing internal cells so juice can be removed more completely in the mills or diffusers. The goal is to maximize surface area while preventing excessive fines that could carry into the juice stream and cause filtration issues. Operators calibrate knife spacing, shredder speed, and hammer settings based on cane type and conditions. Tough, fibrous cane might require more aggressive shredding. Very mature, brittle cane needs gentler handling. Particle size distribution is important. Too coarse and extraction drops. Too fine and screens and clarifiers are overloaded with suspended solids. Some plants use preheating sprays or controlled steam conditioning at this stage to soften the fibers and help sucrose release. Material known after preparation is sometimes called prepared cane. Quality checks, visual inspection, sieve analysis, and small sample extractions verify the preparation stage. Bagasse yield and particle profile are monitored since they directly affect boiler fuel characteristics and downstream diffuser performance if a diffusion system is used. Proper maintenance of blades and hammers is critical. Dull cutters reduce efficiency and increase energy use. A finely tuned preparation line increases juice yield per ton of cane and reduces downstream processing strain. Juice extraction is the core of sugar recovery and occurs by two principal industrial methods: milling and diffusion. Milling remains the most widespread. In milling, a series of heavy, counter-rotating rollers compress prepared cane. Each successive mill squeezes more juice out, while imbibition water is added between mills to wash remaining sucrose from fibers. Modern mills operate in trains of 4 to 7 rollers. Careful pressure control and roller gap settings determine extraction efficiency. Imbibition, adding heated water, recovers sugar left behind in the bagasse and is optimized to minimize dilution while maximizing yield. Diffusion is an alternative where prepared cane passes through a long, counter-current leaching device called a diffuser. Hot water percolates through the cane matrix, progressively leaching sucrose into the aqueous phase. Diffusion can yield high extraction rates and produce more homogeneous juice, but requires consistent preparation and carries different energy and water balances than milling. The immediate outputs are raw cane juice, rich in sucrose, but containing suspended fibers, colloids, and soluble impurities, and bagasse, the fibrous residue. Bagasse characteristics, moisture, fiber length, depend on extraction method and preparation quality, and determine boiler performance. Process control systems continuously monitor flow rates, bricks of juice streams, and bagasse moisture to balance extraction against energy and water use. Efficient extraction maximizes sugar recovery and sets the stage for all clarification and crystallization steps that follow. Bagasse, the fibrous residue after extraction, is not waste in modern mills. It's a primary fuel and energy source. Immediately after extraction, bagasse is conveyed to storage hoppers or directly to the boiler house. Proper handling prevents bridging and allows a controlled feed into combustion systems. Bagasse typically contains 40–50% moisture. Drying in storage, via dewatering presses, or by conveying it through pre-dryers, improves combustion efficiency. In the boiler, house bagasse is burned in high-capacity furnaces to generate high-pressure steam. That steam drives turbines for electricity generation and supplies process heat for evaporators, vacuum pans, and other thermal needs. Many mills operate cogeneration plants where surplus electricity is exported to the grid or used by adjacent industries. This self-generation reduces reliance on fossil fuels and can make a sugar factory nearly energy self-sufficient. Combustion residues ash are collected for safe disposal, or used in limited agricultural applications. Modern boilers include emissions controls to limit particulate and gaseous pollutants. Operational variables like bagasse feed rate, moisture control, and combustion air tuning directly affect steam quality and fuel efficiency. Some mills also blend bagasse with other biomass to stabilize fuel characteristics or pelletize for easier handling. Efficient bagasse management converts what used to be a disposal challenge into a critical asset that powers the factory and improves sustainability. Raw cane juice after extraction carries suspended fibers, small grit and sand, and particulate soils that came with the cane. These abrasives can rapidly wear pumps, evaporator surfaces, and other equipment, and they interfere with clarification effectiveness. Screening and grit removal are therefore early and necessary steps. Screening units use vibrating or rotating screens to trap larger fibers, while grit channels and hydrocyclones separate heavier mineral particles by density. Designs vary. Some plants use a series of coarse screens followed by finer screens and grit classifiers. Operators periodically empty captured grit and inspect screens for tears or blockages. The removed solids combination of sand, stone, and coarse fiber are flushed to waste handling systems. Keeping grit content low not only protects capital equipment but also improves the clarity of juice entering chemical treatment and evaporation. Instrumentation, such as turbidity meters and conductivity probes, monitor juice clarity in real time. Any sudden rise in turbidity typically triggers downstream alarms and may prompt temporary diversion or additional pretreatment. Regular sampling helps mills correlate field conditions, dusty harvest routes, heavy rains, with incoming grit loads so transportation and yard management can be adjusted. Effective grit removal is a small investment that prevents much larger maintenance and efficiency losses down the line. Following initial screening, raw juice is treated chemically to prepare it for clarification. One of the primary interventions is pH adjustment using lime, calcium hydroxide. Juice is heated to approximately 65-75 degrees Celsius to enhance chemical reactions and coagulation. Controlled addition of lime raises pH into a range where impurities, organic colloids, proteins, and fine dirt coagulate into larger flocks that are easier to separate. Lime dosing is measured precisely because over- or under-liming adversely affects sugar recovery and downstream processes. Operators monitor pH, calcium levels, and turbidity. These readings guide lime, flow, and mixing intensity. In some mills, sulfitation is combined with liming. Sulfur dioxide, SO2, is introduced to help reduce color and protect sugar from oxidative darkening. Sulfitation requires gas handling systems and careful venting and neutralization due to SO2's reactivity and regulatory controls. Other additives, polymers, or flocculants may be used to speed settlement or enhance mud dewatering, depending on juice characteristics. Gentle agitation ensures even dispersal of reagents without shredding formed flocks. The objective of treatment is to destabilize impurities and convert dissolved solids into sedimentable forms, producing a cleaner juice that will perform better in evaporation and crystallization. Accurate control here reduces sugar losses and minimizes the load on filters and clarifiers downstream. Clarification removes coagulated impurities from treated juice through gravity, sedimentation, and mechanical assistance. Treated juice enters large clarifier tanks where flocks settle as a dense mud at the bottom, while clear juice accumulates on top. Clarifiers can be conventional circular tanks with slow-moving scrapers or more advanced high-rate units that accelerate settling. Residence time, temperature, and flock size determine clarification effectiveness. As mud accumulates, scraper mechanisms slowly move it to hoppers for dewatering. The settled material filter cake or mud is pressed and often repurposed as agricultural fertilizer because it contains organic matter and some nutrients. Good clarification yields a bright, low turbidity juice that reduces fouling and color load in evaporators and helps achieve cleaner crystallization. Clarifier performance is monitored via sample draws, turbidity meters, and visual checks of clear juice. Operators may perform periodic mud draws to assess solids concentration and to schedule filter press operations. Some mills also use plate and frame filters or rotary drum vacuum filters to dewater the mud further and recover entrained sugar. Efficient clarification reduces sugar losses trapped in the mud and lowers chemical consumption downstream. Because this is a balance of chemistry and hydraulics, chemical dosages, temperature control, and solids management are continuously optimized for consistent results. Evaporation concentrates clarified juice into a thick syrup suitable for crystallization. Multiple effect evaporators are standard, a series of bodies where steam is used progressively so that vapor from one effect supplies heat to the next, improving thermal efficiency. This staged approach minimizes steam consumption while increasing bricks, sugar concentration, from roughly 15% to about 65% solids. Operators control flow rates, pressures, and temperature profiles to prevent caramelization or inversion of sucrose. Fouling on heat transfer surfaces is managed by periodic cleaning and by maintaining appropriate velocities to reduce deposit formation. Vacuum systems sometimes assist in lower temperature evaporation, but multiple effect units are the dominant industrial approach. Concentrated syrup leaves the final effect at the targeted bricks and is sampled for solids, color, and purity before being forwarded to crystallization. Steam economy, measured as kg of steam per ton of evaporated water, is a key performance indicator. Modern plants optimize steam, reuse, and condensate return, reclaiming heat and water for reuse elsewhere in the process. Proper evaporator operation preserves sugar quality and sets the right supersaturation and purity for the vacuum pans. Too dilute, a syrup wastes energy in later stages. Too concentrated risks premature crystallization or degradation. Skilled operators and automated control systems together maintain the delicate balance needed for efficient, high-quality syrup production. Syrup sulfitation is a selective step used in many mills, producing plantation white sugar or aiming for lighter color. Sulfur dioxide, SO2, is sparged into the hot syrup under controlled conditions. SO2 reacts with color-forming compounds and helps reduce oxidative browning. The result is a paler syrup which, when crystallized and refined, yields whiter sugar with fewer decolorization steps. Because SO2 is a reactive gas and a regulated substance, sulfitation requires specialized gas storage, controlled injection systems, and scrubbing of off-gases to protect workers and the environment. Operators precisely meter gas flow based on syrup volume, bricks, and initial color. Monitoring includes sulfur residues and ensuring compliant levels in final products or effluents according to food safety and environmental regulations. Not all mills use sulfitation. Some prefer alternative decolorization techniques, carbon adsorption, ion exchange, to avoid handling SO2. When used, sulfitation often reduces the load on downstream decolorization, saving activation carbon or resin capacity. However, it interacts with subsequent chemistry, affecting pH and calcium balance, so operators adapt clarification and crystallization recipes accordingly. Overall, sulfitation is a targeted tool for color control that, if applied safely and precisely, offers a cost-effective way to improve sugar appearance while minimizing later refining intensity. Its use reflects mill strategy, product specification, and local regulatory frameworks. Crystallization transforms concentrated syrup into solid sugar crystals and is performed in vacuum pans. Under vacuum, boiling occurs at lower temperatures, reducing thermal stress on sugar molecules and allowing better control over crystal formation. Operators seed the syrup with a measured amount of sugar crystals, or seed massaquite, to provide nucleation points. And they carefully control supersaturation so crystals grow at the desired size. The process is staged. First strikes, a massaquite, aim for the highest purity and are harvested for final sugar. Subsequent strikes, B and C, reprocess mother liquors to squeeze more sucrose from remaining solution. Each strike has different target purities and crystal size distributions. Masequite is sampled frequently. Tests include crystal size microscopy, bricks, and purity. Automated controls manage steam and vacuum to keep growth steady. Masequite rheology matters. Overly viscous mixes trap molasses and hinder separation, while too fluid mixes produce fine crystals and reduce centrifuge efficiency. Skilled panmen or modern controllers balance temperature curves and draw off timing. The masequite's mother, liquor, molasses, becomes progressively darker and richer in non-sucrose solids as strikes advance, eventually being used for distillation, animal feed, or discarded under regulated conditions. Proper crystallization maximizes recoverable sugar while producing crystals with the right size and quality for centrifuging and drying. Centrifuging separates solid sugar crystals from the liquid molasses. Masequite is loaded into high-speed basket centrifuges that spin to force molasses out through perforations while retaining crystals. Centrifuge cycles are precisely timed, too short, and crystals retain excess molasses. Too long, and sugar warms or crystals fracture. Many mills apply steam or hot water washes during spinning to displace adhering molasses and improve crystal brightness. Centrifuge operation requires careful balancing and maintenance. Baskets and spindle bearings experience high mechanical stress. Routine inspections, vibration monitoring, and aligned loading prevent failures. The separated molasses is collected and routed for storage or further processing, depending on its purity and the mill's product slate. Centrifuged sugar at this stage is raw sugar, moist, warm, and brownish if not refined. It still contains surface moisture and sometimes remnants of mother liquor, so subsequent drying and cooling are necessary to stabilize the product. Mills track centrifuge performance by measuring residual sucrose in molasses and sugar moisture levels. These metrics guide future pan strikes and washing strategies. Efficient centrifuging maximizes sugar yield, minimizes molasses carryover in crystals, and ensures a consistent feed for drying and grating. After centrifuging, raw sugar crystals are damp and warm. Drying and cooling stabilize them for handling and storage. Drying systems include rotary drum dryers and fluidized bed dryers. Rotary drums tumble crystals while hot air flows through, evaporating surface moisture. Fluidized beds provide rapid, uniform drying by suspending crystals in an upward airflow, which also cools them as moisture evaporates. Process control is critical. Drying temperatures and residence times are set to reach target moisture, typically around 0.1–0.3%, without causing crystal melt or sugar discoloration. Overdrying can create dust and friable sugar. Underdrying risks clumping and microbial growth. Moisture sensors and near-infrared analyzers continuously monitor output so operators can adjust airflow and drum speed. Once dried, sugar passes over cooling conveyors or through chill tunnels to bring temperature down to ambient. Cooled sugar is less likely to agglomerate in storage and travels better on packaging lines. Dust control measures cyclones, bag filters, and enclosed conveyors capture fine particulates and keep the workplace safe. Proper drying and cooling protect product quality and minimize handling losses. They also reduce the risk of caking during warehouse storage and ensure that packaging machinery receives free-flowing, consistent sugar suitable for accurate weighing and sealing. Screening and grading sort sugar into commercial product categories. Vibrating sieves, rotary sifters, and optical sorters separate crystals by size coarse, medium, fine, or prepare sugar for milling into powdered grades. Particle size distribution influences dissolution rates in the consumer's application, mouthfeel in confectionery, and flow properties in packaging. Automated lines channel different grades into distinct chutes and storage bins. Optical inspection systems may check color and foreign particle presence for quality assurance. Samples are routinely analyzed for purity, moisture, and color to certify compliance with product specifications. Grading also supports value maximization. Larger crystals command different markets, while fines can be reprocessed or blended into powdered sugar. Mills may blend batches to meet customer requirements or to smooth variability across production runs. For specialized markets, industrial syrups, bakery sugar, or pharmaceutical-grade sugar, additional processing, washing, recrystallization, or drying adjustments ensures the correct technical properties. Traceability is maintained by recording batch numbers, production times, and grade assignments, which is essential for quality control and recall management. Efficient screening minimizes waste, optimizes product mix, and ensures that downstream packaging receives appropriately classified sugar for accurate filling and labeling. When a refinery is integrated, raw sugar is converted into the highly pure, sparkling white product seen on supermarket shelves. Refining typically begins with affination, washing raw crystals with syrup to remove surface molasses and melting the washed sugar into clear liquor. The liquor then undergoes clarification via phosphatation or carbonation. Reagents cause dissolved impurities to precipitate so they can be filtered out. Decolorization follows using activated carbon adsorption or ion exchange resins to remove color bodies and trace organics. Each decolorization method has trade-offs. Carbon is robust and effective, but requires regeneration or disposal. Resins offer selective removal, but need careful regeneration chemistry. After decolorization, the clean liquor is concentrated and recrystallized in vacuum pans to produce fine, white crystals. This recrystallization step yields a sugar with consistent crystal habit and very low color. The refined crystals are centrifuged, dried, and possibly milled or screened to meet target particle size. Final polishing steps may include steam treatment or controlled storage to stabilize moisture. Throughout refining, strict hygiene and food safety controls apply. Filters and equipment are often more sanitary than raw mill counterparts. Refining adds value but consumes additional energy and consumables. The economics depend on market demand, raw sugar price, and capital availability. When executed well, refining produces a product with superior color, purity, and functional properties for the consumer and industrial markets. Packaging converts finished sugar into saleable units, ranging from bulk 50 kilograms sacks to retail 1 kilogram bags and single-serve sachets. Automated packaging lines begin with bulk storage hoppers that feed screw or vibratory feeders to dose exact weights. Machines then form bags, fill them, seal edges, and apply labels. For large sacks, open-mouth bagging and strap or sew closures are common. For retail, pillow packs or gusseted bags are sealed and boxed. Modern lines integrate check weighers, metal detectors, and barcode printers to ensure quality and traceability. Inline sample stations let quality teams confirm moisture, particle size, and color before palletizing. Palletizers robotic or mechanical stack finished pallets, which then receive stretch, wrap, labels, and shipping marks. Dust control is essential in packaging halls to protect operators and ensure accurate weighing. Hygienic design prevents contamination. Separate lines sometimes handle different product grades or markets to avoid cross-contamination. Packaging materials meet regulatory standards for food contact and provide barrier properties to maintain shelf life. Flexible packaging options allow mills to serve diverse customers. Industrial buyers prefer bulk super sacks. Retailers need retail-ready branding. Food service customers may want intermediate sizes. Efficient packaging reduces product loss, improves logistics, and presents the product attractively to buyers while preserving quality through distribution and shelf life. Finished sugar moves from packaging into dry, climate-controlled warehouses for short-term storage and staging for distribution. Warehouses maintain low humidity and stable temperatures to prevent caking and moisture uptake. FIFO, first in, first out, inventory systems and batch traceability ensure product freshness and simplify quality management and recall response when necessary. Distribution channels vary by market. Industrial customers receive truck or rail bulk shipments. Retailers and wholesalers get palletized loads via freight carriers. Export orders move through port terminals with additional quarantine and documentation requirements. Logistics planning balances production schedules, customer lead times, and transport capacity to avoid overstock or stockouts. For export, documentation, phytosanitary certificates, customs clearance, certificates of analysis is prepared as required by destination countries. Freight handling includes securing pallets, protecting packaging during long transits, and monitoring for moisture or pest risk. Some mills operate dedicated distribution centers that bundle orders, relabel per customer needs, or repack into smaller quantities. Warehouse operations also handle returns and quality holds. If a batch fails to meet specs, it is quarantined for reprocessing or disposition. Efficient storage and distribution reduce lead times, protect product quality, and support customer satisfaction across multiple markets and product formats. Molasses is the dark, viscous liquid that remains after sugar crystals are separated. Rather than waste, molasses is a valuable co-product with several industrial outlets. It is stored in dedicated tanks with heating coils to maintain flowability and prevent crystallization. From storage, molasses can be pumped to fermentation tanks for ethanol production, sold to distilleries for rum and spirits, blended into animal feeds for added energy and palatability, or used as a feedstock for bioprocessing and industrial fermentation. Quality and composition determine its market. B. Molasses, from Second Strikes, is richer in sucrose and often suited for fermentation, while final C. Molasses may be more suitable for feed or fertilizer blends. Molasses also contains nutrients and minerals, making it attractive for rum production and some human food applications after proper processing. Handling molasses requires corrosion-resistant piping, temperature control, and careful inventory management to meet contractual specifications. Some mills upgrade molasses into more valuable derivatives, such as concentrated syrups, yeast feedstocks, or specialty chemicals through additional processing. Environmental controls ensure molasses storage and spills are managed to prevent contamination of soil or waterways. Turning molasses into revenue streams improves overall mill economics and demonstrates how integrated operations can extract more value from every ton of cane. Sustainability is central to modern sugar milling. Energy recovery from bagasse fuels boilers and turbines, producing steam and electricity in cogeneration plants. Efficient steam systems, turbine controls, and condensate recovery maximize energy use while reducing external fuel needs. Excess power often offsets grid demand or supports nearby industries, adding revenue and resilience. Water recycling reduces fresh water demand and limits effluent volumes. Condensate from evaporators and vacuum systems is returned to boilers. Clarified process water is reused for imbibition, washing, or cooling after treatment. Membrane filtration, sedimentation, and biological treatment can polish recycled water to acceptable quality for each use. Closed-loop systems minimize discharge and improve regulatory compliance. Waste minimization practices include using filter cake as soil conditioner, converting ash to construction materials where appropriate, and capturing volatile emissions for treatment. Energy efficiency measures variable speed drives, heat exchanger networks, and process integration reduce overall fuel consumption. Many mills monitor greenhouse gas metrics, water usage per ton of cane, and energy per ton of sugar to drive continuous improvement. Integrated process control systems help orchestrate energy and water flows across the plant for optimal performance. Investing in sustainability not only reduces environmental impact, but often improves profitability through lower utility costs, byproduct valorization, and access to markets that value responsibly produced sugar. Modern mills therefore view energy and water management as central to both operations and long-term viability. If you're enjoying this deep dive into how sugar is made, don't forget to hit the like button, subscribe to the channel, and turn on notifications so you never miss our next industrial walkthrough. Your support helps us create more high-quality educational videos like this one.